Hey everybody, Jonathan here. In this video, I'm giving you my take on section 4.4, which is all about L'Hopital's rule. So, L'Hopital's rule students love because it makes finding a lot of limits much easier. Before now, we could only use algebra to find various limits, but now you can use derivatives to find certain limits. And not only that, certain limits that were not doable with algebra, like ones that involved logarithms or exponential functions, you can do with L'Hopital's rule. So as you all have read by now, at least if you're being the good students that I know you all are, L'Hopital's rule says that whenever you have a function, whenever you have a limit of a quotient, and that quotient is the 0 over 0 or infinity over infinity form, then the limit of f over g will equal the limit of f prime over g prime, provided that any of the limits even exist. Now, students often get confused because L'Hopital's rule only applies to fractions, and it only applies to fractions which are of the infinity over infinity or the 0 over 0 form. And furthermore, L'Hopital's rule kind of encourages certain bad habits, like treating infinity as a number. Well, I've given up trying to stop people trying to treat infinity like a number, but you do have to be very careful because it's not a number, and the standard arithmetic that you do with numbers does not always work with infinity. So first off, let's just clear up. If I write down infinity in some kind of arithmetic expression, it means I am thinking about a limit. It does not exist in and of itself. It's just that I've got some limit, and a part of that limit is going to infinity, and so for short, I'll just write infinity there. So for example, if I write 1 over infinity, it means that, oops, does it circle there? Okay, 1 over infinity. It means that I have some limit in mind, the limit of f over g, where the limit of the top is 1 and the limit of the bottom is infinity. And ooh, look at that extra parenthesis, tragic. So 1 over infinity is an example of what I call a determinate form. A determinate form is one where you know the answer or you almost know the answer no matter what the functions happen to be. If I have a limit of the 1 over infinity form, I know that no matter what functions gave me the limit of 1 in the top and the limit of infinity in the bottom, no matter what those happen to be, the answer will always be 0. And you can kind of puzzle through it. The top is getting very close to the number 1, the bottom is getting arbitrarily large, and something close to 1 over something very large is very small. Therefore, the limit is going to be 0. So it's going to really help your limit skills a lot if you're able to recognize which forms are determinate and which are indeterminate. So determinate forms include things like c over infinity, where c is a non-zero constant. C is any constant. And that'll always just be 0 because you get something that's not necessarily that big over something arbitrarily large. Along a similar vein, if c is not 0, then c over 0 will always be plus or minus infinity. However, when you have actually limits in play, it might actually not exist either. The idea here is that c, whatever it is some number, and you're dividing not by 0, but you're dividing by something arbitrarily close to 0. And as something gets really close to 0, dividing by it makes things really big. And that's going to mean the answer is plus or minus infinity. You can't necessarily say which because 0 here represents a limit. Obviously, you cannot have 0 in the bottom of a fraction. You've known that since like 2nd grade. However, this is, remember, a statement about limits, and it's a limit where the bottom is going to 0. And since the bottom is going to 0 and the top is not, I don't know if the bottom is positive or negative because you can go to 0 from the negative side, you can go to 0 from the positive side, you can go to 0 switching back and forth between being positive and negative. But whatever happens, the limit is going to be plus or minus infinity, or it might not exist. So that's another determinate form. So other useful determinant forms, which are really, you can think of as sort of how to do arithmetic with infinity. Anything of the form infinity plus a constant, or heck, infinity plus infinity for that matter. Now, unlike a determinate form, an indeterminate form is some expression involving infinities, or not necessarily involving infinities, because it could be 0 over 0. If you get something but it's some expression where you cannot say what the limit will be to the infinity, because the limit is going to depend on the actual function. Well, I need to so an example of this would be the infinity minus infinity form. So it is indeterminate because it depends on what the function is going to infinity actually are in order to determine what the value of the limit will will be. For example, the expression x minus
if a
x
is less than 1, then a to
is,
the infinity will be 0.
when you take the limit
that's
as
only
x
when a
goes
is
to
greater
infinity
than
of that, you have a
And
limit
same
of the
here, a to the
infinity minus
minus
infinity
infinity will be
form because
0.
the limit of each part is
As
infinity.
long
But
as
of
a is
course, the
greater
answer
than
is
1.
1.
Obviously
Natural
0.
log of infinity is
On the other
infinity.
hand,
I could do
natural log
something
of 0
silly,
is
like
minus
have x
infinity.
plus
Again,
1 be
all
one
of these are
function
really just
and
statements
minus
about
x be
limits.
another. And now when I take the difference, the answer is obviously 1 because the x's cancel. But before I take the difference, I do have something of the infinity minus infinity form. And then lastly, if you have x squared minus x, both the limit as x goes to infinity of x squared and the limit as x goes to infinity of x is 0. So that is the infinity minus infinity, is infinity. So it is the infinity minus infinity form. However, the limit there is going to be infinite. So we had 3 different examples here, each one of the infinity minus infinity form, but the limit was a different value for each one. Then you have to actually look at the functions. You can't just say what the answer is going to be ahead of time. So the main indeterminate forms, these aren't the only ones, but the main ones we concern ourselves with are infinity over infinity, 0 over 0, infinity minus infinity, 0 times infinity, 0 to the 0, infinity to the 0, and 1 to the infinity. Now, L'Hopital's rule only directly applies to 2 of those forms, the infinity over infinity and 0 over 0 form, in which case the limit will be the limit of the derivatives, provided the limit of the derivatives actually exists. So how can we do L'Hopital's rule on the other forms? Well, you do what you can. You have to somehow get a fraction to show up, and that fraction that shows up has to be of the infinity over infinity or 0 over 0 form. You can't just do something stupid like you did in elementary school and put things over 1 to make it into a fraction. So if you have the infinity minus infinity form, well, in this case, the only thing you can really do is somehow hope some algebraic manipulation will make it into a fraction. And that's completely not guaranteed. In the previous page, we had like the limit as x minus x, and well, there's nothing sensible will get that into a fraction. So you won't use L'Hopital's rule on that particular example. Now, if you get the 0 times infinity form, then you have to do this silly little trick where you write f times g as f over 1 over g, or you write f times g as g over 1 over f. And then if you truly had the 0 times infinity form, you're guaranteed that these 2 fractions will either be the 0 over 0 or infinity over infinity form. However, you can't just, so while you do get something you can do L'Hopital's rule on, you do want to choose carefully here because L'Hopital's rule involves taking derivatives, and derivatives sometimes get more complicated and not less complicated, and if you choose poorly, you'll get something more complicated. And finally, when you have a 0 to the 0 or infinity to the 0 or a 1 to infinity form, you do this silly trick where the limit as x goes to a of f to the g is equal to it's going to equal to e to the limit as x goes to a of g of x times natural log of f of x. The way you see that is you replace f of x to the g of x with e to the f of x, e to the natural log of f of x to the g of x. The g of x comes in front of the natural log like you see right here, and then the limit moves into the exponent because e to the x is a continuous function. All right, well, I hope you have a lot of fun trying all these techniques to do L'Hopital's rule on more than just fractions. Until next time.